Welcome back to our Chem 152 video series. In this video, we'll talk about how to find Ka using percent ionization data. Our problem here says that we have a 0.1 molarity solution of HCN. We'll tell you that it is a weak acid, and that the HCN is 0.0007% ionized. And we are asked, what is the Ka value for HCN? If you're not sure where to start here, try reacting HCN with water and see what you end up making. If we do react HCN with water, we'll start by writing HCN plus H2O. We already know HCN is a weak acid. This means water must act as a weak base. Because it's weak, we'll draw a double arrow. And a weak acid will lose H, leaving Cn behind, and go more negative, making that a negative charge. The base will gain an H to make H3O and become more positive, and so we'll have H3O plus or hydronium. So now we know that if HCN ionizes, it makes Cn negative and hydronium. And now we can think about how much Cn negative and hydronium we've made. To find how much Cn and hydronium we have, we're going to use the percent ionization equation. This equation says that the amount of product ions that we make is equal to the original concentration times the percent ionization. We'll also divide the percent by 100 to get out of percentage and into decimal form. Just bear in mind the Mi I've written here is the initial molarity. In this case, our ions will equal our initial molarity, which was 0.1 molar of HCN. That will go in this first position. We'll multiply that by the percent ionization, which is 0.0007, divided by 100. We can put this into a calculator to find the molarity of our ions. And we end up with 7 times 10 to the negative 7 molarity of both ions. With this information, we can set up an equilibrium table, or ice chart, as some people say. Our initial molarity of HCN is 0.1, and somewhat counterintuitively, we will have 0 to start out with for Cn negative and H3O plus. This answer that we just found using the percent ionization equation tells us that this 7 times 10 to the negative 7th molarity of ions does not tell us what's on the initial line, but rather what's on the equilibrium line. Therefore, in the table, it will go on the bottom row. We will place 7 times 10 to the negative 7th on the bottom row for both Cn negative and H3O. This means that we have now figured out our change here must be positive 7 times 10 to the negative 7 for both. Which means also that our change for HCN must be negative 7 times 10 to the negative 7th. Every time we break HCN into ions, we make some product, but we must use some reactant. However, this change compared to 0.1 is very, very small, which means at equilibrium, we still effectively have 0.1. If you want to put this into a calculator and prove it to yourself, you can. What you'll find is that you'll get almost exactly 0.1 for your answer, and so I'm just going to write 0.1 for our final molarity of HCN. Based on this, we can write a Ka equation, because Ka will equal our products divided by our reactants. Our products are going to be 7 times 10 to the negative 7th, and since we have 2 of them, we'll write squared on top, and on the bottom we'll have 0.1. Then we can place these numbers into a calculator. For our answer, we will get 4.9 times 10 to the negative 12th. That will be our Ka value for HCN. And so this is our final answer for this problem. So this problem showed that using the percent ionization, we can figure out what our equilibrium concentration of the products are, and then using that, find our Ka. Thank you for watching. We'll see you again soon.